So, okay, I have structured this presentation into parts. The first part will be a summary of what the social network interactive, social network benchmark interactive workload for those that have not been present in previous TUC meetings. Sorry for those that will see this once again. And then I will summarize which has been the progress during the last 6 months, which are the future work on this particular workload. Task force members. This is the list of active task force members: Alex Aberbrook from NEO, Moritz Kaufmann from TUC Mission, Marcos Paradis from SAP, me, then Peter and Ori also. They show up time to time and help us with several aspects. And there have been many people from the beginning of the LDBC project that I will not list them here because the list will be endless, but also special thanks to them, for instance, Fam, Duke, Renzo, Norbert, so on. So the interactive workload aims at being a challenging workload, aims at trying to mimic the regular operation of a social network website from a user perspective, and it mainly focuses on interactive queries. Interactive, when we say interactive, we mean queries that can be executed in sub-second and sub-2 seconds time. I will not repeat what Peter said, but basically it's been designed to be flexible, so we are not tied to any specific type of systems and any type of languages. It's been designed for systems that differ different scales, from very small to large. In this case, not only throughput is important, but also latencies, because we want to make sure that the systems implementing these social network websites are responsive, and want to measure this as well. And we also want to make sure that this is easy to adopt. So we try to provide all the facilities and all the tools, so the process of implementing the benchmark is the less tedious as possible. Everything is available in this LDBC GitHub page, from the data generator to the driver, also validation sets that you can use it as your system, and the implementation of the queries, and also all the documentation with the specification. One of the most important parts of this benchmark is the data generator. It tries to create a synthetic social network with many features that you would expect in a real one. I summarize here the most important ones. The first is this correlated graph, in the case of friendships graph. What does it mean? It means that similar people, the attributes of people are correlated among them. So, for instance, if you belong to a specific country, it's more likely that your name will be, it's more probable that your name will be of a subset of names of that country. But also that there is a correlation between the structure and the values of the person. So here what we try to do is to mimic the so-called homophily principle. So similar people have with similar characteristics have a higher probability to be connected among them. So if you analyze a network, you will find that people is connected, has as friends people from that study in the same university, people that have the same interest, and so on and so forth. We also try to model somehow a non-uniform activity volume of the network. So instead, we introduce spikes of activity along the whole simulation time of the social network. So this is try to reproduce the fact that the activity in a real social network is kind of a representation of what happens in the real life. So if something important has happened, like some elections or a very important sports event, then it's likely that people will start talking about this thing in the social network. So we try to reproduce this phenomena as well in the social network. And another very important thing is the scalability of the system, since we are willing to generate very large data sets because we want to test data sets that can handle small, not only small social network websites, but also large websites. We implemented this data generator on top of Apache Hadoop, and everything is implemented based on the MapReduce computing model. And finally, the data generator is deterministic, so you can, regardless of the number regardless of the size of your cluster and the Java virtual machine you use, the output data set will be the same in 2 consecutive executions. These are the size of the currently defined scale factors. Basically, we name the size, the scale factors after the size of the CSV files on disk for the CSV format in gigabytes. So, for instance, if the scale factor 1 it means that it weighs 1 gigabyte of data in your disk. Scale factor 1000 is 1 terabyte of data. These are approximate numbers of the amount of relations and the persons and the messages that are in the data set. The amount of time that the simulation spans. So we see that for the largest scale factor we have defined so far, there are about 20 billion relations with 3 billion messages and 3 billion persons. The data generator outputs the social network into parts. One part, which contains 90% of the total social network, it's that part that will be loaded at boot time. So you will load this data and to your system, and this will be accounted as loading time for the score of the benchmark. The rest, the 10%, will be used to create a set of update events and the update streams that will be used to insert data into the network at runtime of the benchmark. So these are the updates of the social network performed by the users, the content they insert in the network. The idea is that this way we preserve the properties of the social network. That this would be difficult if we inserted this data at random. So this is the motivation of doing this way. And then one important thing is that the data generator also outputs a set of parameter bindings for the queries, for the complex queries of this interactive benchmark, with the goal that the different queries executed will be likely to produce the same execution plan. This is used to try to reduce the variability because we don't want to wrongly select a set of parameters that by mistake or by chance explore a specific region of the graph, and then the query explodes in your face and it's not solvable and dominates the overall workload. So we want some kind of here stability. The benchmark contains 3 types of queries. The first one is what we name complex reads. These complex reads are the fancy queries that I'd say a user would like to do in a social network to explore his neighborhood. They are designed to be, as I said before, interactive, sub-2 second times. They are designed to target a set of choke points the benchmark is shaped around, and more or less all of them have the same shape. So they start from a given node of the graph, explore their neighborhood to get some information and return the results. For example, we have here query 6 that states that given a start person and some tag, we find other tags that occur together with these tags on posts that were created by start persons and friends of friends. So here the point is that the query touches a very small portion of the graph, a neighborhood starting from a given node. We complement these complex queries with a set of short reads. These short reads the goal of the short reads was to balance the ratio between updates and complex reads and reads, and also because they allow us to represent those smaller and simpler queries that the user performs or the website performs to the system in order to fill up the page. For instance, the user clicks at the information of a friend, and then the web page displays this information. Or given a message, we want to fill up the page with the comments to that message, and the information of the likes, so on and so forth. So, for instance, here we have examples. Given a start person, give the first name and last name, the birthday, the IP of a given friend, and finally we have 8 types of update queries, which are those queries used to insert content online into the network, that are basically representative of the content introduced by the users. For instance, I have created a new message, have liked a given post, have created a friendship, so on. Then we have the workload driver. The workload driver is responsible for generating the workload. At the beginning of execution, the driver creates a set of a stream of operations that will be executed based on the for each given person. For each given operation, it's given a start time and scheduled at start time. This means that this is the time that that from the start of execution, this query will be particularly issued, or the driver wants to issue that particular query at that given moment. This stream of operations also contain the type of the queries, and also the parameters that this query will have based on the parameters output by the data generator. The driver also reads the update streams produced by the data generator to issue the queries to issue the queries at the time given by the simulation time of the social network. These are these timestamps that, for instance, for each update stream, for each set of update queries that will be inserted in the dataset, we have this timestamp that is the actual time that during the simulation that this event occurred. So the driver, based on this event, will trigger this particular update at that given moment. In the case of complex reads, as I said, the substitution parameters are read from the dataset files, and this is an important thing, that the time a given complex read will be issued is specified as a multiple of updates. So, in a way that not all queries have the same frequency in terms of updates, because not all the queries have the same complexity. We have queries that are linear with respect to the average degree or the degree of the node. Some of them are quadratic, some of them are cubic. So not all the queries will be issued at the same rate by the driver, because in the end we want to balance in a way that the total time spent per query type in the execution is about the same. So to avoid having a single query that dominates the overall workload. For instance, this is just an example for for scale factor 10. These are the frequencies of the different complex reads, while for scale factor 300, these are the frequencies. We see that, for instance, for query 14, the frequency remains the same, but for query 6, since it's more complex, then it scales differently. Finally, the way short reads are introduced within the workload is the following. We have two types of short reads, those that are person-centric and those that are message-centric. Every time the driver issues a complex read or an update, the driver will also trigger a sequence of short reads. And At each step, every time that the driver issues this sequence of short reads, it throws a coin, and based on a probability that decreases along time, it will show another sequence of short reads. So it tries to mimic the way that a user stalking in the network, so that at some time he will stop his session and stop querying the social network. And in this case, the substitution parameters are taken from the complex read parameters output by the data generator, but also from the results obtained, retrieved by the system when performing the complex queries. The thing why the driver, what we does with the scheduled start times is try to execute the queries on the at the closest time possible to that scheduled start time. The good thing is that we have experimented with the driver, and we have seen that the driver is not a bottleneck of the workload, so it can keep up with hundreds of thousands of operations when he's using different threads with very little overhead. The thing is that these start times are kind of scheduled start times are kind of conditioning the throughput of the workload. So if you think that your system can go faster with a given scale factor, then we have a parameter which is the time compression ratio that allows you to shrink or stretch the workload. So like to play the sequence of operations 2 times faster, 4 times faster, or half the time of the original of the original simulation time. Also, you can configure the number of threads, of worker threads for the queries. And finally, what we have is that with the same driver, we can create validation sets of the execution of the benchmark. So the thing is that using this mode, we create validation sets with different vendors. In that case, we have validation sets for Neo4j and for Sparksy, which we share in our repository, and then we can use them to validate the implementation of our queries by just passing these validation sets to the driver, and the driver will perform the validation automatically. And this is very useful for speed up for assessing the correctness of the queries. Finally, about the execution rules, as I said before, in this case, not only throughput is important, but also the responsiveness of the system, so the latency of the system. So we have set up a rule which says that in order for a benchmark run to be valid, at most 5% of the queries can be executed farther than 1 second of the scheduled start time. So what can happen is that you start execute your system, the benchmark against your system, and your system can keep up with the scheduled start times, which means that when the driver can issue the query, it issues the query because the system is not blocked with another query. But at some time, what can happen is that if the system cannot cope with that rate, at some time the driver will try to start the query at a given scheduled start time, but he will not be able to do so because he will be waiting for another query. So there will be a latency, a delay between the scheduled start time and the actual start times. So this is if this happens to more than 5% of the queries, then it means that your system is not being able to cope with the workload, and then your run will not be valid. Also, we include a recovery test in the benchmark run, in the results, which means that at some point the auditor will shut down your machine and plug it from the power, and all the data that has been reported to be committed must be present there. once the system is up again. And the metrics that we include are latencies for the metrics individually. We report also the throughput. We want to report also the throughput per cost, and also a global benchmark score, including the load time that will also probably divided by the cost in the final proposal. I think this slide, this slide was from our presentation. So now I will move to the progress. 5 minutes, okay, I will try to go faster. We have been, basically, during the last 6 months, we have been focused mainly on improving the adoption of the benchmark. So taking actions in order to make it easier for vendors to adopt the benchmark and try it at least and implement the workload. So the first thing we did was one of the things that we realized, one of the complaints that we had from people was the difficulty of getting datasets from the benchmark. Because the benchmark is built on top of Hadoop, and most of the time people is having troubles not configuring the dataset, but configuring the Hadoop cluster or the Hadoop machine to run the benchmark. So what we decided was to not get rid of Hadoop, but to set up an Amazon S3 bucket with LDBC SMB datasets and interactive datasets for all the scale factors and all the different formats we support. And we just currently set up as a requester pays mode, which means that if you want to download the dataset, you will have to pay the cost of the transfer of the data. We are not making any business here, but it's rather cheap because it's just 3 cents per gigabyte, and the datasets are compressed, so the compression ratio is about 1/3. So downloading a dataset, it's very cheap, about $10 the largest one. And so this is one of the major improvements we have done these last months. Another thing, you see that today it's all about elephants. The second thing we have done is to provide a JDBC driver for those systems that are PostgreSQL compatible. So we have reference implementations with SQL that work and are validated, and it can be found here. So basically, the goal is to serve as a base implementation of the SQL systems, of those SQL systems. And so now if you have a SQL system, you don't have an excuse to download the benchmark. I always put Alex's picture in my presentation in TUC meeting. So this time, I didn't have an elephant, but I had Alex for the progress on the driver. So in this case, we had several requests from users for the driver for some options. We added, in particular, they asked for a possibility to adjust the number of update threads. Currently, the driver only allows you to set up the threads, the number of threads that will issue reads, while the number of update threads were constrained to the number of update streams that were produced by the data generator. So we overcome this issue and added the possibility to adjust the number of threads also for the updates. And another thing that was asked was to be able to skip a set of update streams, so you could restart the benchmark run from a given point. Okay, so you don't have to bulk load all the data set again to start from a specific point. Also, we have cleared a little bit the specification. We have added a couple of sections in the query descriptions, the limit section and the source sections, just to make them more structured and more clearer. and also to make them more consistent with the BA queries that we are currently working on. Also, we have removed a lot of unnecessary stuff from the specifications. We have moved from 106 pages to 39 pages. Basically, we have removed things that were kind of duplicated with respect to content in the GitHub pages, like query implementations, some statistics that are very hard to maintain, and so on and so forth. Instructions on how to configure things that are already in GitHub pages. So now it's more streamlined, I would say, the specification. And yeah, we have released a new version of the data generator. We have added data integrity tests. We have improved the performance and scalability. We have added different ways to configure also the format of the data sets you produce. You can override the way dates and strings are formatted. You can also override the way the content of the messages of social network are generated. This is done for research purposes. Also, you can add weights to the edges in case you wanted to compute to have edges, and also you can override the way these weights can be computed. Also, some bug fixing has been done. For a full list of changes, you can check this changelog. So the future work now is we are going towards the final 1.0 version. We time this for probably after summer. We are preparing new audited results, including Neo4j and Sparksy audited results. Possibly PostgreSQL, we could also add them to the list. But the thing is that these systems are ready, so the implementations are ready. Just a matter of finally finish the definition of the benchmark. Also, we are working on this is just a prototype. We are working on reporting tools. So the driver now outputs a set of log files that can be processed. So what we want to do is to provide a tool that helps to visualize the performance and the time spent of each of the queries, and then helps the user to start understanding a little bit what is going on out there. So these are the conclusions. The detective world of models, the use of a social network side by its users. It's composed by 3 types of queries: complex reads, short reads, and updates. It targets systems at different scales and different kinds, so it's not restricted to a single type of system with a single type of language. We are currently learning a lot from the community, so please send feedback, because now it's the time. So we are close to releasing the first final version, so now it's the time to propose things and before the release, because then it will be much more difficult to do these changes. So once the version 1.0 is ready, this will be sent to the board of the directors, and this will be hopefully accepted by the end of September. So thank you very much, and if you have questions now, I'll be very happy to answer them. Yeah. Microphone better.
The first one is on the snapshot semantics. You mentioned that you have complex read, right? And also you have large graph, and you have concurrent updates. So if there's a complex query going on, and graph is being updated, then the results can be, it depends on how update is being implemented, right? So in that case, do you use a snapshot semantics to determine the benchmark query results?
We have not specified this, because we understand that systems are varied so far and may implement different policies or different protocols for consistency. This has been raised at some point in the task forces that we might discuss this in the future. But so far we are not imposing any kind of consistency model.
Well, read committed is actually acceptable here. And if you look at the business case that's being modeled there, okay, who should I connect to, for example? Who is within 2 steps of me who's got similar interests? That is something that any real system would do in read committed. So there is no strict, insisting on snapshots.
I had another question.
Yeah, the second question is on timeout.
On the?
On timeout.
Timeout.
If you have a set of 100 queries, right, you pump them through to a particular implementation. As we all know, no implementation is perfect, right? Some vendors may choke on a particular query, right, for whatever reason. Okay. In that case, do you just wait, or do you say, hey, after 2 minutes, this is kind of ridiculous, let's kill this one and move on?
Yeah, I mean, if the driver will just get stuck there, the thread, right? Until we do not implement any kind of timeout. So no. Now if your system is not able to answer a particular query, that particular thread of the driver will be blocked, and possibly at some point of the workload it will kind of hang out, right? It can hang or can give the microphone.
So the thing is, the operations all have this scheduled start times, and if your system on a given query, then it can't serve any other query, right? So then it can't keep up with the schedule. Eventually it will finish the slow query, except if the schedule following the query is passed, it will cause you to fail the auditing at the end.
Okay.
So, yeah. It blocks.
Comments, which is for anecdotal purposes, and from talking to a lot of clients and users, please have results also in SQL relational databases, so you can have a baseline, because people who are interested in looking into RDF or graphs, I mean, you give them sometimes and they don't have no idea what that means. They can't compare it to something that they are already aware of. And we've had experiences of talking to people like, oh, we think we have a graph problem. They go test things and they go into it, they try it, and guess what? It was faster in Postgres than anybody else, any of the graph ones. So it's important to have that baseline. So I urge you to put that as a priority too.
Do you think that having a Postgres implementation,
having a relational
implementation
and Postgres more than MySQL.
Okay.
So yeah, I mean MySQL.
Then we will push Moritz to do so. Okay.
I have actually 2 questions. So first, is there any specific reason to have a scale factor maximum to 1000? Is that the size of the output?
It's because it's like we have to set up the proper parameters that will give us. So you don't configure the data generator in terms of the size of the data on disk that we'll have, but you configure based on some parameters, the simulation time, the number of persons. So if we have not defined more or larger scale factors, if we have not, it's because we have not done the process of checking which are the parameters that will produce a data set of that particular size. But we are open to have larger scale factors, of course, because for a Facebook size social networks, 1 terabyte, it's it's not realistic.
Second question is related. Well, you mentioned these parameters. How do you fit these parameters? How do you figure out the proper values? And how do you make sure that generated graph is actually representative?
The generated graph is representative of which parameters?
Real graph. It looks like real at least in some sense.
Basically, we did some experiments on basic characteristics like diameters, size of the diameters, the shape of the distribution, the size of the largest connected component. So what we do is to try to make sure that these measures are actually those that you would expect in a real graph. But ideally, we would like to be very close to Facebook. We try to reproduce that distribution from Facebook, but there is not so much public data that we can try to mimic in this case. But
well, actually, it's interesting because when you increase the scale, the out degree increases, and a lot of the queries are expressed in two-step neighborhoods. So double the scale is not going to be double the two-step neighborhood. It's going to be more like 3 times. There's this kind of logarithmic progression as it gets bigger, then the out degree increases, and scale factors are, analogous, but they're not, it doesn't scale linearly.
Just one last comment. Given that we have Sergey from Facebook and Ori from Google, it would be great if you would eventually become members of the LDVC council. That would give a lot of knowledge from your companies and also would provide a significant amount of work as all the companies that are involved in the LDVC council are doing. So it would be great, I invite you to become members of LDVC. So if there are no more questions,